So on the first day of the gases unit, we did a demo where I took a air freshener, stood in the corner of the room and sprayed it, and had everyone raise their hand when they could smell it. And what we noticed was that it took a very long time for people farther away to smell the gas molecules of the air freshener than people who were closer. Even then, the people that were really close, it still took them, 10, 20, 30 seconds, which contradicts the idea that we know that gas molecules move extremely, extremely fast, on the orders of, hundreds of miles per hour. Okay? There's two main concepts at play here. The first one is diffusion. Okay? So diffusion is exactly what we saw with the air freshener. Diffusion is the mixing of one gas with another as a result of kinetic molecular theory. That's the definition. So think about what we know about the way gases move from kinetic molecular theory. We know that gas molecules move randomly, they move constantly, and they are constantly colliding as well. Lots of collisions. Okay? So since this is true according to kinetic molecular theory, this affects the behavior of a gas and how it diffuses, how it mixes with another gas. What you have in this picture here is a box with a divider, a partition. Just think of another word of that for partition as divider. With one side is empty, has no gas molecules, it's a vacuum. And on the left side here, we do have a gas. And then we remove the partition, we remove the barrier, we take this out. Well, what's going to happen? This is just like spraying the air freshener. Once I click the button down, that's like getting rid of the partition. We know that over time, so some time elapses, okay, over some time, these molecules will diffuse throughout the box. And we've observed that, we've talked about that qualitatively, but what we need to talk about now is what's happening there quantitatively. Okay? And this has to do with something called Graham's law. Graham's law. Graham's law. Okay? And it's a very, very simple concept. The idea is the heavier a gas molecule is, the slower it moves. Another way of saying that is the lighter a gas molecule is, the faster it moves, which makes sense. We're very used to seeing things like that. Smaller cars can move faster. They drive quicker than bigger, heavier cars. And we can represent that with a simple equation. The rate of gas 1 divided by the rate of gas 2 is equal to the square root of the molar mass of gas 2 divided by the molar mass of gas 1. So again, this capital M is the molar mass in grams per mole. So what this is saying is if we want to compare the speeds at which two gases mix, their rates, okay, we need to know the molar masses of those those two gases. Or if we know any three of these variables here, 1, 2, 3, we can figure out the fourth just with a little bit of algebra. That is diffusion. A new concept that we haven't talked about yet is effusion with an E. E-F-F-U-S-I-O-N. Effusion. The difference between effusion and diffusion is actually quite simple. In effusion, what we are doing is we are separating gases, okay, where the partition has a small hole in it, okay? So we're not actually getting rid of the partition, we're not getting rid of the barrier between a gas and another gas. We've made a little hole that allows some molecules to move through and others maybe not to. And what we can see is what this depends on, the likelihood that, let's say, this molecule here gets through that hole depends on how fast it moves. Because we know that this molecule is going to move all over the place. It's going to bounce, boom, hit other molecules, hit the wall, boom, boom. Eventually, it's going to go through that hole. And the idea is, once again, the faster that molecule is, the faster it's going to go through this hole and effuse, with an E, to the other side. The slower the gas molecule moves, the longer it's going to take for it to effuse to the other side. Okay? So what's cool about this is you could have two different gases on, this side. If we have this container here, okay, with a little partition, we could have one gas that has a certain molar mass and another gas that has a different molar mass. And let's say blue weighs a lot more than green. Its molar mass is a lot heavier. Well, the idea is if the molar mass of blue is a lot greater, it's going to move a lot slower. And if it moves slower, it's not going to effuse through this hole as quickly as the green one will. So what we would see over time, actually, this is kind of a separation technique that we can use to separate two different gases from a mixture, is over time, we would see the green, lighter, faster gas molecules separate from the blue ones because they move a lot faster. So that is the difference between effusion and diffusion. Okay? In effusion, there's a small hole separating the two sides of a container. It allows us to separate two gases in a mixture. Whereas diffusion is just the removal of this partition, and just we can observe what happens to the gases as they move throughout the whole open space. In class, we'll talk about how to do some quantitative problems, but you need to know the definitions when you walk away from this video. You need to know this equation and what each variable means, and we'll talk about some qualitative problems tomorrow when you come in for the launch to distinguish between the two different processes.